Hello everyone, I am Sai Avinash. So I completed my 6 weeks training program of Intro to Autonomous Mobility at LHP Columbus. So first I would like to introduce myself. So I recently graduated from IUPUI with Masters in Mechanical Engineering, and I have an industrial experience in automotive industry where I designed batteries for electric trucks. And also, I've done many projects regarding automotive control, such as automated emergency braking and CAD designs, as well as projects on Python as well. So, in this PowerPoint, I'm gonna first give an introduction about the autonomous mobility and why I took this course. Then I'm gonna talk about the sensors which I work here, like such as the sonar, camera, vision, LiDAR, and I will talk about the fusion and why it is needed. Later, I will conclude my experience with this PowerPoint, and finally, I'm going to talk about the future plans of me. So, as we know that autonomous vehicle or self-driving car is a vehicle which senses its environment by its own, and it does not require any human help. So, for sensing this environment, it requires many sensors, such as LiDAR, camera, sonar, and radar. As we can see in this picture, like each sensor is used for different features. For example, the camera is used for the lane keeping system, and sonar is used for the forward collision warning as well as park assistant, and LiDAR can be used for the emergency brake system, collision avoidance, and radar can be used for the adaptive cruise control. So during this course, first we got an introduction about the CAN SAE J1939, in which is like communication between the vehicle parts, and also we got an overview of the ISO 26262, which is the functional safety. So next, I'm going to talk about the sonar, which is like sound navigation and ranging. So for this, we use the HCSR04 ultrasonic sensor. These are some technical specifications of that sensor, which the power supply is 5 volts DC, the measuring angle is 30 degrees, and the ranging distance is 1 to 30 feet. So for this, I considered 3 ultrasonic sensors, and I placed it in the front of the vehicle in such a way that there is a difference between 10 degrees of each 3 sensors. So as you can see in the middle picture, it was arranged in such a way that it can be used for the forward collision warning, as well as we can do it for same as rear. And as we know that ultrasonic sensor is used like transmit the sound waves first, and when it detects an object, the receiver will receive the sound waves. So from this sensor, we will get the time, and we had a know as the speed as 343 meters per second square. So from the formula of speed is equal to distance by time, we will get the distance. Next, camera vision. So for camera vision, we use the Logitech USB cam. So the main purpose of the camera vision is like following the yellow line. And my car has a steering angle starting from 45 to 145, and I divided the whole frame into 16 parts. So for each part, I given a certain angle from 45 to 145. So as you can see in the left side is the raw image that was captured by the camera on the car, and we are programmed such a way that it can only see the yellow color and yellow line. So it will follow the yellow line. Similarly, we have done the same with the red stop sign. So whenever it sees the red color stop sign, it detects the stop sign and it will stop. So here is a video of camera vision which is following the yellow line. As you can see, it will always tries to be in the follow the yellow line, and it says to be in the center. Next, LiDAR. It's light detection and ranging. So for this sensor, we use the 2D laser scanner RP LiDAR A1 as a sensor, and the distance range of the LiDAR will be like 0.15 to 12 meters, and the angular range, so it will detect 360 degrees, and the sample duration will be like 0.5 milliseconds. So LiDAR, as I said in the second slide, LiDAR is used for the avoid the collision. So for this, I consider only 180 degrees. So the front and side part will be considered, and I gave some minimum distance so that whenever there is an object in that distance, it will try to avoid it. And I defined the steering angle as straight, slight left, straight right, and similar to the left. So here's the video of LiDAR. As you can see that it will always try to be in the center of those two cardboards. So whenever there is an detects like less than 0.4 meters, it will try to go to the other side. Next, fusion. So why fusion? As I said earlier, the camera is used only for following the yellow line. So whenever there is an object on the yellow line, it will either stop or it will hit. So for LiDAR, it will detect the object, but it can't follow the yellow line. So in the fusion, we will combine the LiDAR and the camera such a way that it follows the yellow line, as well as in the same time, whenever there is an object in front of it, it will try to avoid it. So it's the video. As the it's following the yellow line, whenever there is an object placed, it's trying to avoid it. So conclusion. So like I really got a hands-on experience with the various sensors in this training, and why I chose is LHP is like I found like similar online courses regarding the sensors, but those are all predefined data, so we'll be working on them. But in LHP, we are working with the sensors, and we are interpreting and implementing the data from the sensors. So it will be like mainly hands-on experience. So we got to know the errors and everything. So, and also during this course, the communication between my fellow trainee and the TA as well as other interns, it has really helped me to get this training. So whenever I got a question or any problem regarding the code, they are really helping us. Next, I faced some problems in this training, such as like while I was working with the sonar sensor, the servo motor, which is used for acceleration, I was not able to operate it. So when I go into that, when I was checking with the manual, so I got to know about those motor, and I try to fix that. And whenever I have problem with any particular thing, I will just Google it and I will try to solve the problems. So that really helped me in this course, as well as time management. So whenever I was like behind the schedule, or whenever I was going to learn a new thing for the next day, I used to go after the office hours. I used to go home and allocate some time so that I will be prepared for the next day. So these things really helped me to complete the course within the time frame. So for future plans, I would like some. I was planning to work on the radar in detail. We worked with radar in this course, but there is like more. We have to get it. So, and I also like to use the 3D LiDAR instead of 2D. We use here 2D LiDAR. So I feel that if we use 3D LiDAR, the results will be more accurate. And implementing the radar in the fusion along with camera and LiDAR, so that whenever there is an object here, it goes right and it will slow it and slightly turns. So that will be like really helpful. And there are other sensors used in autonomous mobility such as GPS and IMU. So I would like to get hands-on experience with those as well. Thank you all. Next, my fellow trainee Akshat will continue his presentation.
Good afternoon, everybody, and thank you for being here. And I would like to thank LHP for giving us this opportunity to learn and develop our skills. So a little bit about myself. I have a master's in electrical engineering from Stony Brook University. I graduated in December. During my master's, I have 2 years of project experience using machine learning and deep learning. I I joined LHP to use these skills. Also, during my bachelor's, I worked as a COO for 3 years in my family business. So I developed management skills and other business development skills over there. In this presentation, we'll go through some things which we learned in the course, such as Agile, ROS, Sonar, Camera, LiDAR, Y-Fusion, future work, and conclusion. So during our first week, we were introduced to the Agile Manifesto and Scrum. I really tried to use the Agile Manifesto and the principles whenever I can throughout the course. The two most important principles I used were welcome changing requirements and deliver working software frequently. So all my codes are written in a function basis. So at the end of each day, even if the whole program was not ready, some of the functions were ready. And each day there was a software or part of the code which was running. Along with that, changing requirements. So currently we are using a 2D LiDAR. So my algorithm works for a 2D LiDAR, but by just making few changes in the code, we can make it work with the 3D LiDAR so that we don't have to write the whole algorithm again. So ROS. ROS is an open source. We use ROS for our robots. It is a meta operating system for the robot. What it allows us to do is test our developed features correctly in a safe environment basically, and help finding flaws in the algorithm. So the first sensor we used was Sonar. The main important part here is checking the range, which is 2 centimeters up to 4 meters. So this is not a very accurate sensor. It gives good values only in this range. Above 4 meters, it doesn't work. So the applications I developed using the Sonar were park assist, collision prevention, and blind spot detection. Here's an example how the blind spot detection works. So the sensor is faced at the side view mirror, where it is facing the other lanes, the lanes which are not in the view of the rear view mirror. And if an object is detected, if a car is detected, it blinks the light or it rings our alarm, whatever we want it to do. Next, we used a camera. So for camera, the field of view is 60 degrees. So the applications developed using camera are lane detection, object detection, and classification. Here's an example how the lane detection and lane following is working. It also helps us give us a lane departure warning. Here's how the internal algorithm is working. So first, the stop sign is detected. After that, the stop sign is marked. Similarly, for the lanes, these yellow lanes are detected and these pink lines are drawn by the algorithm itself. And using these pink lines, the steering angle is calculated and sent directly to the wheels. Everything here is autonomous basically. Nothing is pre-calculated. Next, we use the LiDAR, whose range is from 15 centimeters up to 12 meters and a precision of less than 0.5 millimeters. So this is a very accurate sensor. The only drawback we have is that it is a 2D LiDAR, so any object which is not in its line of sight won't be detected. I'm really proud of my algorithm for LiDAR. It is a good achievement that I did at LHP. So how this works is our bot is 27 centimeters wide. And if there's a window of 40 centimeters, the bot can go through it. So I decided the window should be 40 centimeters and at least 50 centimeters away, that is the height of the triangle. So at least 50 centimeters away, it should decide whether it can go through that or not. So using simple trigonometry, I decided the angle, which was 40 degrees. As long as there are no objects in this triangle, this window will exist and the bot can go through. So here's a good example. All these objects are actually out of this 50 centimeters range. The LiDAR could have chosen this part, this, or this one. But it chose this part because it sees up to 12 meters. So the algorithm is actually calculating the best path, not at that moment, but like it can see up to 12 meters, as I said. So in the long duration, what would be the best route for it? So after this angle is calculated, it is sent directly to the wheels. So that was one of the challenges, getting the correct turning angles. Okay, fine, I've got the angle from LiDAR. How do I pass it to the wheels? So for this, I implemented a PI controller where these angles from LiDAR are ratioed and changed according to the turning angles of the wheel. Also, getting the correct window size was really important, whether it should be 40 centimeters or 30 or 50, we didn't know. So to get the correct window size for our track, the technical way would have been to develop a simulation using Gazebo, which would have taken at least 2 hours. But we found a simple way. I took the help of my teammate Sai. We went to the track. We literally just used an inch tape or a measuring tape and a few rulers. So we got a rough estimate of the angle and the bot works well. Also, the time complexity here is really important. Time complexity basically is how well the algorithm works, how fast the algorithm is. So the current time complexity of the algorithm is O of n, which is fast, I would say. So when we are using a 3D LiDAR, the data points will increase from 360 to around 12,000. So if the time complexity is bad, then the algorithm will be slow and we won't be able to use that data properly. Here's the video of LiDAR, how it is working. It finds the best part automatically and just follows it. So fusion, as Sai indicated, why fusion is required, because measuring distance from the camera is not an easy job and it's not accurate. So now we have a LiDAR. LiDAR can measure the distances. So we use the LiDAR and camera to detect the object using camera, following the lanes, using the camera, and the LiDAR measures the distance of the object. So the application is developed for lane change assist and path planning. Here's how it works. So the car was following this lane. As soon as it detects another object, it switches lane and it starts following the other lane. If there were no lanes on the left side, the car would have just stopped. So the challenges faced while the fusion were the field of view of the camera and bot did not match up. Also, we are using a 2D LiDAR, so the camera height and the LiDAR should have matched perfectly. Otherwise, object detection would have been a little more difficult. So when I place the camera parallel to the floor, it has a dead zone of 60 centimeters. With respect to the car, it's a lot. But in a real world scenario, 60 centimeters is nothing because the hood of the car will cover up that space. So for this, we tilted the angles and we prevented the car from turning earlier than needed. After this future work, I would say is I would like to work more on radar and GPS. And I have a couple of algorithms in mind, which would be adaptive focus control, which would work as radar can see much further than anything and it can measure the speed of other objects. We can develop an algorithm which would judge the speed of other objects and change our car speed. Also, using GPS localization can be done really well, which will help in our fusion case as lane change assist and other things will work even better. So concluding, we have developed these ADAS features such as lane detection, blind spot detection, prevention, path planning, lane change assist, and park assist throughout the course. Also during the training, I've improved on my skills such as teamwork, time management, communication, critical thinking, and analysis. So whenever I used to think of an algorithm, I always used to pitch up to my TA, Elsa, and teammates and other interns around here. And I used to get their view of what they think about the algorithm. This helped me finding flaws in the algorithm before I implemented it so that it is perfect when it is implemented. And it helped me explain things better to them. So any questions for us?